PN junction diode. Actually, my subject is electron device and circuit. From that, I am going to discuss about first topic, that is PN junction diode. In that, I am going to discuss about energy band diagrams of PN junction. Okay, let us see here energy band diagram of PN junction. As you know, previously we learned in some topics in physical engineering, nothing but the engineering physics. There are two types of elements we observe: p-type and n-type semiconductor materials. Here, this is the p-type material. When we go to the p-type semiconductor material, there are majority charge particles are holes and minority charge particles are electrons. Coming to n-type semiconductor material, here the majority are electrons and minority are holes. So how these, here the p-type semiconductor material, the trivalent impurity atoms are doped into this p-type semiconductor material. Here the n-type material, there are pentavalent impurity atoms. There are pentavalent impurity atoms are available here. Basically, the n-type device having the property, the donor property. Here the p-type is in the acceptor property. So coming to the energy band diagram of this p-type semiconductor material and n-type semiconductor material. Let us see here the energy levels or energy band. So here it is nothing but valence band region. This is nothing but conduction band region for p-type. Let us see here, this is the energy, forbidden energy level for the p-type semiconductor material. And here, this is the Fermi level, energy of the Fermi level for p-type. Here it is located near to the or over to the valence band of p-type semiconductor material. Coming to the n-type semiconductor material energy band diagram, it is the valence band. This is nothing but conduction band. Here it is the forbidden energy gap for n-type semiconductor material. Similarly, p-type semiconductor material, here located the Fermi level of this n-type semiconductor material located near to the conduction band. Here it is a Fermi level for n-type, it is listed here, but I was located here, it is a energy level for Fermi. It is located near to the conduction band. Why this Fermi level, energy of the Fermi level located to this valence band in p-type and conduction band in n-type? Because of here, coming to p-type, here the majority charge particles are in valence band or holes, and the minority charge particles are electrons. The majority charge particles are holes and the minority charge particles are electrons. So due to the concentration of the majority charge particles, the energy of the Fermi level is located near to the valence band. Similarly, in n-type semiconductor material, as I told you here, the majority charge particles are electrons. That's why the concentration of these majority charge particles are more compared to minority charge particles in n-type semiconductor material. That's why here the energy of the Fermi level is located near the conduction band of n-type semiconductor material. Next, let us see here. We know in p-type the majority number of charge are holes compared to electrons. That's why the Fermi level moves closer to the valence band. Similarly, in n-type, also the Fermi level is close to the conduction because of the majority electrons. Let us see the energy band diagram of p-type and n-type material in the next slide. This is the energy band diagram for P-type semiconductor material, and here energy band diagram for N-type semiconductor material. As I told you previously, in valence band, the major charged particles are holes. So here the concentration of charged particle is more due to the major charged particles. That's why the energy of the Fermi level is closer to the valence band. Okay. Here, if you are applying any external energy, if you are applying any external energy, then electron gain some energy and jump from valence band to conduction band. This is the energy. If you are applying external energy, that energy above this energy gap, if your applied energy is above this energy gap, then only the electrons are jump from valence band to conduction band. Okay. Similarly, so here let us see here again in n-type semiconductor material. Similarly, as p-type, the Fermi level is located below the conduction band. So because here the major charge particles are electrons, that's why it is located at the junction. And this is the energy gap. So generally, the energy gap of this n-type material is 1.12 electron volt. Okay. This is the energy gap. Let us see here the energy gap for silicon material. It is 1.21 electron volt at 0 degrees Kelvin. At temperature at 0 degrees Kelvin. At room temperature, that is 300 K, at room temperature, the silicon electron volt is, that is energy gap potential voltage, electron volt. It is dependent on electron volt, that is 1.1 electron volt. Similarly, for germanium, the energy gap is 0.78 electron volt at 0 degrees K. Similarly, and at room temperature is range is 0.72 electron volt. So in p-type material, the Fermi level is above the valence band because the holes are more. Okay, next. In first slide, we are observing p-type material and n-type material. Now, these two materials are joined together by some diffusion process. Combining these two materials, then it is formed as a p-n junction. But actually, there is some concept behind this to form this p-n junction diode. What is that? First of all, we can take one silicon crystal material, uniform silicon crystal material. For that material, we can diffuse doping the trivalent impurity atoms, that is one side, that is nothing but p-type material. Similarly, in other side, we doping the other material, that is trivalent impurity atoms, in other side, then it is formed as the n-type region. Here, the region, how this region is formed, this region nothing but depletion region. Okay, this is p-type material and this is n-type material. These two are combined to each other. Now, how this region is formed here? Okay, I told you. So, in this region, this is the p-type region. In p-type material, there are majority charged particles are holes, minority charged particles are electrons. Coming to n side, the majority charged particles are electrons and minority charged particles are holes. Okay, so how this region is formed? What is the basic concept behind this? Okay, let us observe this. If you dope the trivalent impurity atoms in some area, that area is here, we are saying it is p-type region. The concentration of holes are more. Similarly, the concentration of electrons are more in n side. They are diffusing towards the junction. Due to the concentration gradient. Diffusion. What is going to be diffusion? They are the concentration gradient from higher concentration gradient to lower concentration gradient. The electrons are moving from, or whatever it may be, the charged particles are moving from higher carrier concentration gradient to lower carrier concentration gradient. Then the current is flowing. That is the diffusion. So due to the diffusion, when the holes are moving from p side to n side, then the holes are nothing but positively charged ion particles. The electrons are negatively charged particles. When the holes are moving from p region to n region, then near the junction they leave the negatively charged ions. Similarly, in n region, the majority charged particles are electrons here. When they enter, here the concentration gradient of electron is more, here the concentration of gradient of electrons is less. So due to that, the concentration gradient is very high here. Then the electrons are moving towards the P junction, P region. Then at the near the junction, they leave the positively charged ions. Okay. Due to this, the depletion region formed here. Similarly, we can say it is a barrier region. So due to these, here let us observe here. These are the negatively charged particles. These are the positively charged particles formed near to the junction. So there is a electric field, and this electric field generated, and then here the potential due to this electric field there is a potential is formed here. This is the negative polarity. Here it is the positive polarity. This is the electric potential is formed here. This electric potential or electric field does not passes to the remaining charged particles through this region. Whatever those are majority charged particles here, the majority charged particles here, those does not passes through this particular junction. Because of this barrier junction here act as a brick or a wall. That's why it doesn't pass the remaining charged particle from P side to N side and N side to P side. That is the basic concept of this particular PM junction diode. So let us see other the points here. When it form a PN junction, there exists a non-uniform concentration carrier. That is, the holes are more in P type, the electrons are more in N type. When there exists a non-uniform concentration, diffusion will take place. That means that the holes from P to N side and electrons from N side to P side. They are moving from P side to N side to P side, such as majority charge carriers. When these positive ions are moved from P side to N side, they leave negative ions near the junction. Similarly, the electrons move N to P side and then they leave positive ions near to the junction. This region is called depletion region. But due to negative and positive charge carriers across the junction, an internal electric field is generated. The electric field is directed towards from N side to P side. Okay, that will show next slide. The electric field is directed towards from positive side to negative side. Everywhere, the electric field is direction is from positive side to negative side. From positive side to negative side. Okay, so let us see here. We have seen an electric field is generated, then the potential difference is also be developed. Okay, I told you that when the electric field is generated here, then the potential difference also developed here. That potential difference is nothing but here the negative polarity here, positive polarity is here. So due to that, potential difference is then developed by the electric field. So due to that, the minority charge carriers are moving towards the direction. The minority charge carrier here nothing but holes. They are moving towards the direction. The minority charge carrier here electrons, such as moving from P side to N side. So that current, there is a movement of minority charge carriers through this junction. Then that current is nothing but drift current. Okay. Right. Let us observe here 2 points: diffusion current and drift current. The diffusion current is generated due to the higher carrier concentration to lower carrier concentration. The charged particles are moving. Due to that, the current is generated nothing but diffusion current. And due to the minority charge carriers, are moving from P side to N side to P side, then the drift current is generated. So here diffusion current and drift current, due to that it is neutralized. Here these ions are immobile ions. Okay, let's go to the next slide. here. So finally, the diffusion of electrons and holes will be stopped by the internal electric field, or we can say the junction potential or built-in potential. That's why in equilibrium there is no current. Okay, as I told you, here there is a it is immobile, and these immobiles are is nothing but depletion region or barrier region or built-in region also, or cutoff region, cutoff sorry, cut-in region of in junction layer. So when this region forms, the remaining charge particles, such as major charge particles, and here major charge does not pass through this particular region because of it is in equilibrium condition without applying any external forces. Okay, that's why in equilibrium there is no current. Initially there is a diffusion, but later the diffusion current will be cancelled by drift current due to the internal electric field. Okay, so this is the formation of P-N junction diode. Okay, that is the basic concept behind this to form the P region and N region and the diffusion region. So let us do the explanation, or let us observe the explanation of energy band diagram. So this is the energy band diagram. Here, as I told you previously, the electric field is moving from directed towards from positive direction to negative direction, and the voltage is negative direction to potential negative direction to positive direction. Okay, so let us see here. This is the conduction band in P type and valence band in P type. Similarly, conduction band in N type, valence band in N type. Okay. As I told you, first slide. Go to the first slide now. See here. Okay. This is the energy band diagram for P type and energy band diagram for N type. Let us see here. See the energy band, energy gap for P type, energy gap for the N type. So when here majority charge particles are holes, here the majority charge particles are electrons. When the electrons are moved from N type to P type, then what happens here? They leave the positively charged particle here. So then the positively charged particle is here, then the Fermi level of this N type material is moved away from the conduction. Similarly, when the positively charged particles are moved here, such as holes, they are moved from P side to N side, then it leaves the negatively charged particles or increases. So then it is the energy of the Fermi level is moved away from the towards close to the conduction band of P. So now just for the energy band diagram for this, just it is moved downwards, it is moved upwards. Now let us observe the energy band diagram for PN junction. Let us see here. So the electrons are moved from conduction band, N-type conduction band. Okay, those are majority charge particles here. Those are moved from N side to P side, then leave donor ions, but nothing but positive ions here. So how this bend is occurs? This part is nothing but P type, this part is nothing but N type. Okay, this part is nothing but P type material, this part is nothing but N type material. These are the energy levels. These are the energy level for N type and P type. As I told you in the first slide. Now, how this band is formed, bending is formed in this particular energy band diagram. This bending. Okay. When the electrons are moved from this side to this side, then the positive ions are increases near to the junction. Increasing means it is increases exponentially like this. So here, the positively charged ions are moving from P side to N side, then it leaves the negatively charged particle near to the junction at equilibrium condition. Then it is the decreasing this level. So this bending is on. Okay. So this is the energy band diagram. So certain point, the concentration of this N-type material and the concentration of P-type materials are equal. So then the energy levels, energy of the Fermi level is equal. Okay, so let us see here. This is a constant energy, energy of the Fermi level. Here it is at equilibrium. Equilibrium condition means the concentration gradient is here, the concentration gradient is here. Those are equal. So the Fermi level is equal for both p-type and n-type material. Okay, this region nothing but depletion region. Next slide. This is the energy band diagram for equilibrium condition of p-n junction line. Suppose if you apply any external forces, means here for positive direction, for positive charge particle, here you can apply the negative. For positive area you can apply the positive. Here it is a negative charge particle. For negative you can apply the negative terminal here. So means if you are applying any external voltage, by using like battery, then what happen here? The positive charge particles are moving towards the direction and the negative charge are moving towards the direction. Nothing but generally we say it is forward bias, forward bias of the PN junction there. Okay. Then what happened? So here generally let us observe the energy band diagram. This is the voltage, electron voltage required. As I told you, the electrons are jumped from one conduction band to one band to another band. There are two bands, valence band and conduction band. When the electrons, whatever it may be, when the electrons are moving from valence band to conduction band, how they jump from valence band to conduction band? There is a certain amount of external voltage or external energy is applied, then only the electrons are jumped from valence band to conduction band. So that amount of voltage is here, nothing but this is voltage in here denoted as E V naught, electron volt. Okay, electron volt. So this amount of electron voltage is required to jump the electrons from this band to this side, P side. Okay, so that amount of voltage, that amount of electron voltage reduces for forward bias and increases for some other, that is reverse bias condition. Let us see the diagrams also. So here, let us see here, this is for forward bias condition of P junction energy band diagram. Okay, so here, again, same concept, the electrons are moved from P side, N side to P side, they lose the positive charge particles at near the junction. They are the increasing order. The bend is formed here. So this is the electron volt, required electron volt. The electrons are jumped from P N side to P side. This electron volt nothing but is a charge here. V nothing but potential difference. That is VB minus V0. VB nothing but barrier voltage here. As I told in previous class, previous slide, there is a potential difference that is also called as barrier voltage, barrier region. That is nothing but barrier voltage. Here, V0 is nothing but you are applied, it is applied external voltage using battery. That is denoted as V0. The difference between VB minus V0 is the required potential voltage to jump the charge particle from this area to this area. So it is the very less amount of electron voltage required to jump the charge particle from this side to this side. So means in previous slide the gap is very more. Now here the gap is very less. But here there is no difference to look at here. But there is a difference practically when we have to discuss this type of formula. VB minus V0 is nothing but very less amount of electron voltage required to jump the charge particle from this side to this side. So coming to forward bias condition, so here VB plus V0. Reverse bias condition VB plus V0. Okay, VB plus V0 is nothing but it is the increases the electron volt here, charge into voltage difference. But here the voltage difference is nothing but VB plus V0. This voltage will be increases. So means the gap is also increases. So means the large amount of electron voltage is required to jump the charge particle from N side to P side. Okay, see here. In this energy band diagram, the electrons move from N-type conduction to P-type conduction band. Okay. By gaining the some energy, that is electron volt, to be found in the forward bias and reverse bias condition of PN junction diagram. The energy band diagram in forward bias and reverse bias. In forward bias, the electron volt is EV equal to Vp minus E naught, so that the energy gap is reduced. In reverse bias is EV equal to Vp plus V naught, energy gap is increasing. Okay, so this is the overview of the how the P-type metal is formed, how the N-type metal is formed, how they are combined to each other, and how the depletion region is formed. Okay, what is the drift current, what is the diffusion current, okay, what is the energy levels of the energy band diagram for equilibrium condition, nothing but without applying any external forces to the particular PN junction there. And also, if you are applying any external forces, then also you can observe the energy band diagram for PN junction there. So this is the overview concept of energy band diagram of PN junction. Okay.